Welcome to the NPTEL Power System Protection course. So, we are in module 2 on phasor estimation, and in this lecture we will address how decaying DC becomes an issue to phasor estimation techniques and what is the mitigation strategy for that. So, continuing with that, let us take an equivalent system. We have a voltage source and a transmission line also can be model, approximate model have resistance and inductance, and then a fault is triggered. So, this is RL transient. In that case, the corresponding system equation, voltage being sinusoidal, expressions can be like this, and the corresponding IT during this fault period will be sin omega t plus theta minus theta z plus minus sin theta minus theta z e to the power minus t by tau, where tau is the time constant, that is L by R of the circuit, and theta z, which is we see here in from these two expression, is tan inverse x by r, where x is omega L by r, omega corresponds to the fundamental component. Now, note that in this transient current we have an exponential term, and this you can say that exponential term. So, it is an exponential decaying term, and this is steady current, sinusoidal current. So, this is voltage sinusoidal, this is current sinusoidal. So, this part you can say that as theta is also fixed and theta z also fixed depending upon the L and R. So, this part is a constant term, and this you can say the exponential term. So, this part you can say that is nothing but that decaying DC part. So, we see that for a sinusoidal signal, voltage signal, if a fault happens to be there, the current is expected to have sinusoidal plus decaying DC part. So, this a typical signal here, this is the before fault current, pre fault current, fault is incepted at 1 second in this case, and then you can say that we have a current signal like this, steady state, sinusoidal current only. In this transient period, it has a decaying DC component, and that is what this component is doing in addition to this sinusoidal part. So, this with large time t, this part vanishes. So, this becomes 0. So, therefore, this part becomes no more contributing to the signal. Here in this case, how this considered component becomes influencing, we will see that theta minus theta z, this part sinusoidal. So, n pi, then this becomes 0. So, 0 transient, only sinusoidal signal, sinusoidal current signal also, no decaying DC. So, n 0 1 2 3. So, this becomes 0. Theta minus theta z, this becomes pi by 2 factor sinusoidal, that becomes 1. So, this maximum transient will be for n equals to 1, 3, 5 and so multiple of pi by 2. So, that becomes you can say that prominent, the decaying DC will be prominent in that case, and the decaying DC is not available for this case. So, however, the switching event theta, the switching the event will depend upon the at what instant it is being switched on. So, accordingly you consider the magnitude of decaying DC will be coming to picture to this corresponding current signal. Note that this decaying DC part is even an exponential part. What we have discussed in frequency response is either harmonics, interharmonics or complete only DC, not exponential term, not decaying DC. So, how good is the frequency, how good the corresponding phasor estimation technique to this challenge now, that you have to see. So, this is what you can say that from here we see that depending upon the fall inception, depending upon the location, and depending upon you can say that different types of fall, and so this you can say that corresponding relay will be observing you can say the decaying DC component, and this is an additional component to the sinusoidal component. Our target is to capture the fundamental from this part. So, this modulates the signal, this component modulates the signal. So, therefore, what we say here is that we like to consider that use the corresponding things in that manner. So, to the purpose you can say that how influencing this part is to the phasor estimation technique. So, when this becomes significant for this n pi by 2 perspective, then we see that the current magnitude will be affected, and therefore, you can say that overcurrent relay, distance relay, and so which use the corresponding fundamental component current are expected to you can say that malfunction or so. So, to avoid that you can say that we need solution mitigation strategy, how to you can say that they eliminate the corresponding decaying DC part from the fundamental phasor estimation process. For that we have you can say that a concept called mimic filter. Let us see you can say that what happens using this approach. First we will talk about analog filter, and then we can say that we will go to the digital mimic filter. So, this is the current which is there during the transient process, this fault current in the primary side, and that is being injected to you can say that to an R and L combination, R dash and L dash combinations. So, this fault current is being injected to an R dash and L combinations, and we are taking the output of this you can say that V 0 t to the you can say that to the relay side. So, this part you can say that it is called the mimic impedance. Now, how this corresponding circuit is useful you can say that we will see that. So, let the decaying DC current is I t equal to e to the power minus t by tau. This tau is the time constant L by R of the power system circuit, as we have seen in the earlier slide. So, therefore, this V 0 S the output voltage here Laplace transform of that will be S L dash plus R dash into I s into this I s. So, Laplace inverse of this voltage which will give us the V 0 t equals to Laplace inverse of S L dash plus R dash divided by S plus 1 by tau. Now, when the tau that is L by R of the system matches with L dash by R dash, that is what this filter we have put in this circuit in the connecting to the relay circuit. When the tau the time constant of the power system matches with the time constant of this additional circuit which we have put here, in that case we see that from this expression this becomes also with taking out L dash. So, Laplace inverse S plus 1 by tau, and the denominator also we have S plus 1 by tau with this condition, and that becomes you can say that we need L dash the corresponding Laplace inverse of 1, that becomes you can say it gives you the unity impulse. So, the decaying DC output in the V 0 t I t constant decaying DC, that is the power system, but if we connect the corresponding signal to R dash and L dash with condition that L dash by R dash equals to the time constant of the power system circuit, then the output of the consider this in voltage terms that does not contain any decaying DC. That is the beauty of the this filtering process, and this part you can say is called the mimic impedance, mimicking the power system circuit in terms of the perspective of tau equals to L dash by R dash, and then you can say that this process eliminates the decaying DC part. Now, if you see this you can say that performance wise, so this is what you can say that if you use the without mimic filter and with mimic filter. Mimic filter introduces, because this is RL combinations, a phase lag perspective. So, we have you can say that these corresponding things. Without mimic filter we have the black one, they having a decaying DC. With mimic filter you can say that we have the blue one, and then you can say that the corresponding decaying DC part you can say that is almost overcome, problem is overcome in this case, that is what we say, but there is a phase displacement due to the presence of the L circuit in terms of that. So, this we can say that is the that has to be compensated in the computational process. Now, extending this idea of putting an R dash and L dash in the circuit, that is a mimic filter, you can emulate this, you can say that to the digital filter also. Now, let us see with mimic filter consisting of RL combinations and which is nothing but represented in terms of Laplace transform into k 1 plus s tau, tau the time constant of the circuit. Then the exponentially decaying component of the output will vanish, that is what we observe, and with the time constant tau matching with the L dash and R dash. So, the S term in this is nothing but acts as a differentiator circuit, and that can be considered with a digital filter. We can consider 1 minus Z inverse. So, substituting S by 1 minus Z inverse, we can this impedance becomes equals to k 1 plus tau minus tau Z inverse. For k has to be set such that you can say that because our target is the phasor estimation. So, therefore, the filter gain has to we can say to be 1 for that 50 or 60 hertz nominal frequency. So, in that case we can say that we have from these relations k 1 plus tau minus tau e to the minus j omega t, that magnitude of that should be equals to 1 for the corresponding 50 or 60 hertz frequency. In our case earlier examples we are considering 50 hertz nominal frequency. So, solving this equation we got k square, the gain part k square equals to in terms of this. So, the real and the imaginary part, where n capital N you can say corresponds to the number of samples per cycle, and thus you can say that using the mimic filtering concept, if you say you can say that from this perspective. So, the perspective. So, this signal output from the mimic filter I dash p, that equals to k 1 plus tau into I p, the present sample, minus tau into the just past sample. So, this previous sample. So, this I p into 1 plus tau and I p minus 1 into tau. So, for the pth instance the corresponding output you can say that. So, then in that case this you can say that signal will be having no more decaying DC component. So, this differential current present sample just past samples leads to you can say that with this weightage you can say that will lead to you can say that elimination of the decaying DC component successfully. This is what is the digital mimic filtering approach. However, if you see this gain, then the for a particular nominal frequency the gain you can say it becomes 1, it has an imaginary and a real component. So, the phase you can say that shift by the mimic filter which we see in the analog domain also, that becomes equal to tan inverse in the digital domain, the imaginary part divided by the real part. So, this you can say that phase shifting can be obtained, and that can be compensated you can say that in the digital platform. So, by doing that compensating, we have two plots you can say that without mimic filter and using a digital mimic filter with phase compensation. We say that the black one is you can say that it without mimic filter. So, it has a decaying DC component, and with digital mimic filter and compensating this phase, then we get you can say that the corresponding blue one with the dotted you can say that one. So, we see that it has overcome the decaying DC part, and also you can say that the phase is being compensated. So, therefore, the relay you can say that can the current signal you can say that will does not require any further change in angle and so as compared to the voltage also. Note that you can say that such you can say that decaying exponential decaying part is we have demonstrated here for the current, but that can be that can also happen in case of voltage also, particularly when it is using the capacitor voltage transformer. When the fault happens to be close to that, the corresponding output signal contains exponential decaying part. So, in that case also we can put such perspective you can say that to overcome the issue to extract the fundamental component successfully. Now, what we say here that in the above discussion that the one cycle DFT which is having you can say that will be influenced by the you can say that decaying DC part can integrate such you can say that digital mimic filter or analog mimic filter before processing for phasor estimation technique. Now, we will see consider how the corresponding decaying DC can be incorporated in the least square estimation modeling perspective, and how it can consider successfully eliminate the decaying DC part. So, we know from the our earlier consider discussion that the signal the decaying DC signal is an exponential term, and then we have a sinusoidal component. So, therefore, at nth sample the corresponding signal can be I sin omega t n plus theta plus k 0 e to the power minus t n by tau. So, we can model the corresponding signal fault signals, this fault component with a consider decaying DC component and a sinusoidal component as you see. Now, in this case the corresponding I, the corresponding theta and the k naught and the corresponding tau are the unknowns you can say that in this signal which are which need to be considered estimated to get the corresponding fundamental. Our target here consider to get the fundamental component correctly. Now, if we expand this, you can say that in the using the Taylor series, then this k 0 e to the power minus t n by n, that becomes equals to k 0 minus k 0 t n by tau plus k 0 t n square plus 2 factorial tau square and like that. So, approximating for this series and neglecting higher order terms, we first only consider these first two. If you require more accuracy, you can extend it take it to more further terms also. So, considering only first two terms, that these you can say decaying DC part can be k naught minus k naught t n by tau. So, therefore, expressing this corresponding current I n equals to I sin omega t n cos theta plus I sin theta cos omega t n plus k 0 minus k 0 t n by tau. So, this is about that decaying DC part, this is for the sinusoidal part. If you remember in least square estimation technique, you use the consider same, you consider this part you consider as earlier. Now, we will say to consider the unknown you consider vector and the corresponding A matrix and so. So, unknown vector becomes you consider like earlier case for the sinusoidal part I cos theta here and I sin theta here. So, x 1 equals to I cos theta and x 2 equals to I sin theta, two unknowns, and x 3 equals to take it k naught and x 4 equals to consider it take k naught by tau. Agree? So, this you consider these are the four unknowns in this signal we like to estimate in our least square formulation, and the corresponding A small a coefficients for this system for this signal model sin omega t n, cos omega t n, 1 for this and a n for minus t n. So, if you multiply this a and you can say that the corresponding x, then we will be getting the signal. So, in that fashion you can say that we say can say that in this case we have considered 4 unknowns 1, 2, 3 and 4 unknowns, and we have 1, 2, 3, 4 in the A matrix, and like that you can say that if we take n from 0 to consider that n you can say that samples, then you multiply this you can say that a into x, then we are getting you can say that I 0 to I n you can say that the n plus 1 you can say samples in the measurement process. So, we say you can say that A x equals to m, and this you can say that is the corresponding signal model perspective for the system. So, we know you can say that A you can say that is available to us like we did for the phasor estimation using least square estimation techniques. X is to be found out, m you can say that measurements or the samples of the currents are available to us. So, therefore, the x the unknown vector becomes you can say that left pseudo inverse of this part into the measurement vector. So, then you can say that from there you can find out the I x 1 square plus x 2 square root over theta you can say that tan inverse x 2 by x 1. Note that for the computing the RMS value like you did for the in phasor estimation technique also, if you divide by root 2 we will be getting this corresponding RMS value. For example, in the least square you can say in the presence of decaying DC, how good is the least square estimation technique in eliminating the decaying DC, we can evaluate here. Let us take a signal I n 100 sin 100 pi t n, that is 50 hertz plus 30 degree plus 250 e to the minus t n by 40. Some you can say that decaying DC, large value of decaying DC in this case. and this Tn is n delta t you consider same, you can say that which we have considered for this 400 hertz sampling rate for the 50 hertz system. So, using first 4 sample points only, that is half cycle least square part, because we have 4 unknowns. So, at least we require 4 samples. So, we consider the 4 measurements like this for this signal, and then the A matrix you can say that we construct using as we have defined, because we say you can say that A x equals to m. So, this you can say that the 4 cross 4 matrix for this for different timings, and the corresponding measurements you can say that we have taken this. So, therefore, you can say that we say here that the A matrix obtained you can say that becomes this from the time information, and then x you can say that the 4 you can say that unknowns are to be computed. So, from the least square you can say that we apply this formula, and then you can say that we estimated the x to be considered from this relation to be these 4 values. So, this corresponds to I cos theta, I sin theta, k naught and the k naught by tau, and from there you can say that from these first two you can say that we get the corresponding estimated value x 1 plus x 2 square you can say that, and then finally, the RMS value to be 70.7, and we say that the estimated current phasor you can say that 70.7 30 degree is the correct phasor, because if we see here you can say that this current signal which we have considered here is 100 sin this. So, this is the fundamental part, this is the decaying DC part. So, even the corresponding signal is being contaminated by this decaying DC, this 100 by root 2 is nothing but 70.7, that we correctly got the phasors by using this least square technique, where we have modeled the decaying DC component in the least square approach. So, thus we see that you can say that least square estimation technique is able to eliminate the decaying DC component successfully. So, Inovalor remarks that decaying DC components can remain you can say that in the current signals, and which may affect the performance of the phasor estimation technique unless it is being filtered out. If it is not being filtered out and affects the phasor estimation technique, then the relay performance will be affected, like distance relay can see with higher current under each issue, over current may find saturations with CT saturation issue, and also you can say that the over current may have a coordination problem and so. So, to mitigate you can say that such things, we have mimic filter both analog and digital, along with you can say DFT if you use, then decaying DC can be eliminated, and the cosine filter has is inherent you can say that the suppressing the decaying DC component also, which we have already talked earlier also. In least square technique with proper modeling, we can overcome the decaying DC component. So, this is all for the phasor estimation techniques. Thank you.